What if gravity is non-local? Meaning, what causes the curvature of a local spacetime is not that local mass and energy, but it is something happening non-locally far away that is causing the local curvature. What if the matter and energy of, say, a star is spread out non-locally far away, and something happens to these non-local things that cause the curvature around that star? Because matter and energy are equivalent, there must be something non-locally equivalent to whatever that local matter and energy must be. Look at these coils, and I want you to imagine that these coils are entangled particles. One is spinning clockwise and the other is spinning counterclockwise, and the tissue paper is to represent the entanglement. Now I want you to imagine two types of entanglement, one that breaks easily and one that does not break easily. Now, as you can see, when I interact with the top coil, the paper rips. When I interact with the bottom coil, the paper instead warps. Now I want you to imagine that this flat entanglement tissue paper is a flat spacetime, okay? So because the spacetime is warping, let's put a particle here with mass, because we know that mass warps spacetime. So it was the transfer of angular momentum from my hand to the coil which slowed it down, causing the warping between these two entangled particles. And so this is a type of non-local interaction that may be happening, which is slowing down the angular momentum of all of these non-local particles around a local object, which is causing the warping. And this slowing down, this type of interaction, must be equivalent to what that local mass is. The warping of spacetime might not be dependent on a local mass, but the non-local interactions relative to that local mass, which we perceive as a local curvature of spacetime. Here is another analogy that may help explain what I'm trying to talk about. Now, in this example, there is no particles, there's no curvature, nothing is happening. Let's say our mission is to measure a particle, like an electron. Now, we can't really see any particles in this example yet. If I fold the paper over, I want this to represent an entanglement between two particles, the first non-local field. So we have two particles that are quantumly entangled. We could say that this particle up here is spin up and this one is spin down. And we know that particles are excitations of probabilistic waves. So something like this. Now again, these entanglements existed before we measured the particle. Why don't we add another fold to the paper? And this is to represent two pairs of entangled particles. This adds another layer of non-local particles interacting with the second field, which warps the spacetime around the local center. And so, what if this is what's happening when we are interacting with particles? And maybe this could explain the wave-particle duality, is that there is a certain amount of non-local particles interacting for a specific type of energy. Like there is a certain amount of non-local interactions happening all at the same time to cause a local curvature, and it might be finite based on this wave-particle duality, because when we subtract a field of entangled particles, we only have one, then we don't see anything, we just see waves, and we don't see anything localized. But when we add a layer, we see a localized point where a particle may be when we interact with it. And so that may mean that when we interact with a particle here, we are causing these non-local particles to interact with this field to break the wave-like nature of particles. Here I'm going to do a little double slit experiment. So here is my particle beam. So the particle is traveling like a wave through the double slits, interfering with itself, creating the interference pattern. So now, when the particle interacts with our detector, now let's fold the paper in half and let's see what happens. We see, because we've added a layer of non-local entanglement interaction, we are creating localized points in space-time, which we can perceive as distinct energy levels when it hits the screen. And these intersections of these entanglement fields are probabilistic. Say the particle ends up right here. If the particle is right here, when we interact with it, with the detector, we are non-locally interacting with this entanglement field at that moment of measurement. And so this is like lighting up a part of non-local space-time that when it interacts with itself will localize certain particles and energy levels. It's really crazy to think about. And now this particle has even more mass. Would you look at that? How cool is that? And you can see how there are more non-local interactions building up as we give these particles more mass. Okay, and here's our last particle. And look at all of these entanglements and how many non-local interactions there must be for a particle of this mass. I mean, this is crazy. So it's pretty cool when you stack them up. You can see how space-time builds based on the number of these non-local interactions. So could this mean that for every point in space-time, there is a certain number of these entanglements passing through that point? And when we're measuring certain particles, they would have a certain number of non-local interactions for that particle. So, for example, maybe all electrons have two pairs of entangled particles, and a heavier particle would have, three pairs. So now, if we have two particles that then interact with each other, both of their fields, what's going to happen? Well, I have no idea. But what if they clump up? And maybe that could explain dark matter. So, for example, the non-local particles for this particle is interacting with non-local particles for another particle. I don't have two spicy chickens, I only have one. When these particles interact with each other, they clump up on this axis and not this axis, or down there, but this axis. You know what I'm saying? This clumping would cause the curvature for this particle and the next and the next. So it's really these non-local interactions that influence the space-time that we see. Not really, I'm just saying, like, that would be cool though, right? Like, if I feel like this kind of makes sense, that there could be a whole non-local aspect to gravity. And, well, what if there is a non-local aspect to the other three forces? Because, well, they are local interactions, right? But what if for each force there is something happening non-locally that represents that force? If we go back to the coil analogy, instead of momentarily interacting with the coil to make it like kind of warp, if we just held our hand there all day long, the paper would warp like crazy, and it would just be all over the factory, and it would just make it a massive mess. So what if this is happening for a black hole, where the interactions basically stop the angular momentum of the coils or the particles non-locally around that dying star? Then it might cause the curvature of space-time to go into these infinities, because the paper is just going everywhere and it's just basically building up. Because of quantum mechanics and entanglement, because our universe is non-locally real, these entanglements cause the universe to become real. I hope I helped you understand what I was envisioning here, that gravity may be non-local, and that the local curvature of matter and energy as we know it may have been an illusion all along.